Hi everyone, this lecture will walk you through the revision of the basic concepts for storage elements, including latch, flip-flops, registers, and also counter. I will also guide you how to put some of the components in Verilog. Digital circuits are comprised of combinational and sequential circuits. So the figure shows the combinational circuit that depends on the input to produce the outputs, while for sequential circuits, on top of the combinational logic, it has the storage elements such as flip-flops and latches. For sequential circuits, it can be further divided into two types: synchronous sequential circuit and asynchronous sequential circuit. This lecture will focus on synchronous sequential circuit, which has clock as a global signal that synchronizes the transfer of the next state to the parallel state. Combinational logic, as mentioned briefly just now, have outputs that depend on only the input and do not have memory, meaning they cannot store data or state in the circuit. Sequential circuit, on the other hand, have outputs that depends on the input value as well as the past state or past behavior. So the past state is stored by the storage elements. The content of these storage elements is normally called the state. So we call here what is stored is the present state, and what will be stored next, which appear at the input of the storage element, is the next state. So the circuit will go through a sequence of states when the input change. For synchronous circuits, which is one type of the sequential circuit I mentioned earlier, the components inside the circuit operate in synchronous with a global signal called clock. So in synchronous circuit design, we need to ensure that the data signals, the data that's stored at the flip-flop input, the data signal need to be stabilized within a specific time window relative to the clock signal. So this is to ensure the reliable data capture by the flip-flop or register when the clock trigger. So this is an important characteristic and timing analysis we need to perform if we choose synchronous sequential circuit method for the design. For asynchronous circuit, it doesn't have the clock component like flip-flops. The circuit output and state change independently and independent from any global signal, and potentially making them faster because the transfer of the data from one point to another point doesn't need to wait for the clock. However, it is harder to design and analyze. So it doesn't operate with a global clock. Instead, it has some local handshaking signals between the components to tell whether the data transfer is performed successfully, or to tell whether some data is needed and requested from a component. Instead of flip-flop, it has an element called delay elements. So this one is very important because the delay element is to adjust to ensure the proper timing and synchronization of the signal to prevent the hazards such as the race condition, glitches, or even the metastability situation. Looking at the gate level, the delay element can be realized by adding the buffers. This slide shows a simple example of a synchronous sequential circuit. It consists of a sensor that tries to detect some vibration, and then it also connects to an alarm. Okay? So basically, it's a security system where it detects a vibration and turn on the alarm. So how the memory plays the role in this sequential circuit? When the sensor sends a vibration, even a short one, this signal that showing the vibration will be stored by the memory elements and turn on the alarm as long as it is needed. So how that happen? So in other words, if the vibration create a short pulse, it doesn't mean the alarm will be turned on for a short while, thanks to the memory element that store the on state of the vibration to turn on the alarm until somebody come and reset the alarm. Basic storage such as latch is made from gates. The example of shown here is SR latch, which consists of two NOR gates. This latch is an active high latch because it has R indicate reset when R equal to 1 and S equal to 0. So while S is assigned 1 and R is assigned 0, it indicates set, where the latch will have Q equal to 1, which means set. So it has 3 modes as shown here, where 0, 0 means Q will stay the same as the previous value, 0, 1 means Q will become reset or 0, 1, 0 means Q will become 1 or set. 1, 1 is not allowed, or it is an invalid state. Why 1, 1 is not allowed? When you assign 1, 1 to R and S, both of the outputs Q and Q bar will become 0. You can simulate and see. And one of the reasons why 1, 1 is not allowed, because the resulting 0, 0 at Q and Q bar contradicts with the design of the latch, where Q and Q bar should complement with each other, or should be the inversion of each other. The second reason why 1, 1 is not allowed in the SR latch is because if you put 1, 1 followed by 0, 0, what will happen to the circuit is the 0, 0 will invert the Q and Q bar to 1. Now you can see the toggling happen from 0 to 1 at the output side. So even you keep the 0, 0 at the input side, which is supposed to mean hold in the correct functionality, but because of the previous signal 1, 1 we assigned, the continuous 0 here will not play the role of holding the Q. Instead, the continuing 0, 0 will keep toggling the output Q and Q bar, and it generate the race condition. So you will see theoretically race condition will continue forever as long as R is 0 and S is 0. However, luckily in realistic in the actual situation, thanks to the process variation of the fabrication of the gates, even these two gates are the same gates, which are NOR gates, but the delay that this NOR gate has is slightly different from the other NOR gate. So because of that, when the race condition happen, some delay may result in the slightly late 1 coming out at Q bar compared to Q, if we assume the lower NOR gate has longer delay. Okay. So the accumulated delay will make the difference bigger, and at one point when the delay is longer, then the circuit of the NOR gates here, the pair of NOR gates here, will eventually see the difference value, which is 0 in this case and 1 for the second NOR gates, and it will eventually settle the latch into the stable 1, 0. Okay, so remember the race condition is because the two NOR gates keep observing the same value along with the R equal to 0 and S equal to 0. But if there are slight delay happen here that produce the Q bar slightly late, the accumulated delay will eventually cause the two different values to be observed by the respective NOR gates, and it will settle the Q and Q bar to the complement values. As shown in this figure, it will settle to 1, 0. This is another version of the latch, but this one is made from NAND gates. Okay? So NAND gates will make the latch active low, where the Q is set to 1 only when S equal to 0. Okay? Because it's an active low. 0 become Q equal to 1, and when R equal to 0, then it's a reset, which Q will become 0. So this is another version of SR latch, where apart from input S indicating set and R indicating reset, there is an additional input called enable input. So this enable input plays the role to turn on the SR latch or turn off. When enable equal to 0, as shown on the first row of the truth table of the SR latch, you will see that when SR latch is disabled, there's no change at the output Q. So in other words, it's like holding the value Q as per the previous value. So when enable is 1, then the SR latch will work like the active high SR latch, where when R equal to 1, it's reset, and when S equal to 1, it is set. So when two inputs S and R are tied to together through the inverter. So the gated D latch is formed. Okay. So gated D latch overcome the limitation of SR latch. So as you remember, SR latch has the illegal state or the input SR11, which is not allowed, or illegal inputs. So but when you connect S and R together through the inverter as shown here, you make the eliminate the illegal output state. So when gated D latch is enabled, then the Q value will just follow the input value D. So when D0, Q equal to 0. When D1, Q equal to 1. Okay? So D can be considered as a data, where this latch is a data latch that just latch in whatever value at D to the output. As you can see here, we can use the graphical symbol as shown here to represent a gated latch, and you will see that it is a level sensitive latch because whenever enable equal to 1, Q will change according to D. Okay? So for instance, Q stay as 1 here because D is 1. And in the second slot, when enable equal to 1, Q is 0 because D is 0. Look at the T3, when enable equal to 1 again here, the change of D from 1 to 0 will also propagate to the Q. However, there is a transparency issue in the D latch. So as you can see in the shown in this waveform, whenever enable input is high, the output will change according to the input. So if any data that is need to be transferred to Q and stay as a stable signal, the transparency scenario will cause a glitch that happen at the input side to be propagated to the output as well. So in other words, the input keeps changing state also mean the output change continuously. So to control that output change only once, we need to control the input D to stay stable during the transfer or when during the latch enable. So to ensure that there's only one transition during the transfer from D to Q, we have to use another solution, which is flip-flops. Flip-flops can be divided into master-slave flip-flop and edge-triggered flip-flop. Master-slave flip-flop consists of two stages, master latch and slave latch. The output change when the clock pulse finish or when the clock pulse drop from 1 to 0. That means when the clock pulse happen, when the clock rise, the input is allowed to go into the master slave flip-flop, but the finalized output will only appear at the output queue after the clock pulse finish. Whereas for each trigger flip-flop, the transfer of the data from D to Q happen only during the clock level change, which is the rising edge or the falling edge. Let's look at how the operation of master-slave D flip-flop perform. First, master-slave flip-flop consists of master latch and slave latch. So these two are the gated latch, where the enable input is getting the signal from clock, and the second latch enable input get the signal from the inverted clock. So what happens is when the pulse is applied through the clock, which is labeled C here actually refers to the clock here. When the pulse is applied, first what happens is the data will move from D to inside the slave clock, which is QM. You can see more obviously during this pulse. Okay? When this pulse start, and during C equal to 1, the data, which is 0, will go into the latch at QM, and you can see a 0 here. But during the pulse, when the data change along the duration of pulse, the QM, which is in the middle of the flip-flop, also change. But the output is also is only finalized when the pulse ends, when the clock falls. So at the time when clock falls, then the final value of D, which is 1 here, will be transferred to as a final output at Q or QS. Okay. So that's why sometimes in some reference, master slave D flip-flop is also known as pulse-based D flip-flop, because it works based on the pulse. When pulse happen, the data to be transferred will go inside the flip-flop and then reaching Q as a final output after the pulse ends. From the time the pulse ends until the next pulse happens, the output does not change. So in other words, the transition is only happen during the pulse. So that means some transparency issues still there, because if the pulse is not narrow, is wide enough, we still can see the glitch still propagate from D to Q. So the second type of flip-flop called edge-triggered D flip-flop transfer only the data on the edge, which is better because it eliminates totally the glitch to propagate from D to Q. So let's see how the edge-triggered D flip-flop works. It consists of 3 pairs of NAND gates. First, let's look at when clock equal to 0. When clock equal to 0, when you simulate the 0 with the NAND number 2 and NAND gate number 3, you get signal 1 at P1 and signal 1 at P2. And let's assume the data value is represented by D here. So together with the clock equal to 0, the data will propagate to P4 as D bar, through this wire as D bar, and also through the wire to and NAND gate 1 as D bar. So D bar and 1, we get D at P3. See, the last stage of the pair of NAND gates is the RS latch. So when clock equal to 0, this NAND based RS latch have P1 equal to 1, P2 equal to 1, which put the latch in hold mode. In other words, when clock is 0, there's no change happen to the D flip-flop. Q will stay as the same as the previous value. But at the point of time when clock rise, which is at the point of the rising edge, what happened to the circuit is 1 is okay. Let's put 1 here and simulate it. Then we get D bar at P1. Okay, the 1 with the D, we get D bar. Also, then 1 and D bar after NAND gate inverted to D. So let's look at this. What happened to this RS latch when we have D bar and D on the rising edge of the clock? So as the symbol bar shows, D bar and D are complement to each other. So the RS latch, when complement to each other, meaning there's a 0 here and 1 here, or 1 here, 0 here. So the RS latch here is either in the set mode where Q equal to 1 or reset mode where Q equal to 0. So if you check here, let's say when D equal to 1, it will put the RS latch in the set mode because D bar means 0 and this is 1. Okay, so if 0 is simulated with the NAND gate 5, then Q become 1, okay, and then the other side will become complement, which is 0. So when D is 1, okay, then the RS latch is put in the set mode, then Q become 1. So that is exactly the same like how what we understand about the behavior of the D flip-flop. When D equal to 1, Q will become 1 when the clock edge rise. Okay, it's opposite. In opposite scenario, when D equal to 0, then P1 will become 1, P2 becomes 0, which put this NAND RS latch into reset mode, where Q will become 0 on the rise of the edge. So the change happened, the transition happened, or the change at the output happened on the edge. So when the clock stably stay at 1, what happened is it is no more transferring the change of D to Q. Instead, it will stay as D bar D or until the clock falls to 0. So that is how the edge-triggered flip-flop works. So now this slide shows the waveform that show the different behavior between the gated latch, okay, and positive edge-triggered flip-flop, negative edge-triggered flip-flop. Please check your understanding on the differences among them. The latch output QA change according to D when clock is 1. Positive edge-triggered output B, QB, change on the rise of the clock. And negative edge, D flip-flop, change on the fall on the negative edge of the clock. A JT flip-flop is a versatile sequential logic storage with 2 inputs J and K that can toggle, set, reset, or hold its mode based on the input condition as listed here under J and K. But it is not used much in VLSI design. Instead, it is more common for electronic discrete circuit where you buy the JK flip-flop in a chip or IC form and then plug in on the PCB or the breadboard to build an electronic discrete circuit. T flip-flop is a type of flip-flop that toggles its output on each clock pulse when the single input T is high and maintain its current state when the T is low. Okay, so when T is low, previous state. T is high, toggling. It also doesn't exist in chip form. Normally, you can use a T flip-flop with the additional circuit to build a T flip-flop. And it is more commonly used in making or developing a counter. So the slide here show the standard symbol for SR latch, active low SR latch, D latch, gated D latch with active high control, gated D latch with active low control. This show the symbols for the positive edge triggered flip-flop, negative edge triggered flip-flop, positive edge triggered JK flip-flop, negative edge triggered JK flip-flop. So in addition to the D flip-flop basic version, you also may see that the D flip-flop equipped with the asynchronous set and reset, or asynchronous preset and clear. Okay, so set means preset, reset means clear. So preset, clear. So D flip-flop with preset and clear inputs allow asynchronous control of the output, where the preset input set Q equal to 1, while the clear input reset Q to 0, independent of the clock signal. In other words, it doesn't need to wait for the clock trigger to set or reset the Q immediately. These inputs are typically active low with a bubble here showing active low and take priority over the input and clock signal. Now let's see how do we code the flip-flop and latch in Verilog. The new syntax or Verilog construct I would like to introduce here because it is a necessary keyword to be used in describing the flip-flop. It is post edge and negative edge. Post edge refers to the rising edge of the clock signal, named clock, where a flip-flop updates its output based on the clock, okay, and making it edge triggered. So you need to, when you code a sequential circuit that works synchronously with the clock, then you have to, after the always block add, you have to put in the sensitivity list post edge clock. Similarly, if the operation is based on the negative edge or falling edge of the clock, then you have to use keyword neg edge, which refer to the falling edge of the clock signal, triggering the flip-flop to evaluate its input change at its input and change its state when the clock falls. Okay. Whereas for D latch, if you recall the truth table for the gated D latch, it is as shown here. So when you want to code the Verilog for D latch, you can base on the truth table. So from the truth table, it shows that when enable equal to 1, Q exactly follow D. But when enable equal to 0, there's no change. So you can put here, you can use if enable equal to 1, Q equal to D. In the sensitivity list, we put the signal that will determine or play the role to decide the Q value. You may ask why there's no else like this, right? Because just now I said else means when enable equal to 0, it should stay Q equal to Q, right? When enable equal to 0, Q equal to Q, no change. You can write else like this, or you don't need to have else, because this else Q equal to Q, which means retain the state. Okay, so this part of statement is not necessary, because Verilog default behavior, it will retain the last value of the output when no assignment occurs during the simulation. So you only state what happened to Q if n equal to 1. If you don't have else Q to Q, the simulation will assume so, because that is the default behavior. Okay, so in other words, for D latch, you can just shorten your coding this way. Okay, the else one is no need, because the compiler has assumed the Q retains if no statement given here. For flip-flop, which is a negative edge triggered, then as mentioned earlier, you can use neg edge clock to show during the fall edge of the clock, then this behavior happened, where during the clock fall, only the data will move from D to Q, okay, as shown in this waveform. When clock drop, okay, so D1 will transfer to Q. Okay, it doesn't transfer before the clock fall. If you want to code the D flip-flop with asynchronous reset, You can do so where the difference is you put the negative edge reset together with the positive edge clock in the sensitivity list, which indicate that the Q output of the D flip-flop will change when clock trigger to positive edge or clock rise, or when the reset is changed to 0. Okay. So this will describe the asynchronous inputs, where when RSD, the reset, equal to 0, okay, checking by this condition, so immediately without waiting for the clock, Q will become 0. Else it will wait for the clock to transfer the D to Q. This is as shown in this simulation waveform, where you can see when without reset, then the clock rise will transfer the value D equal to 1 here, just before the clock rise, D equal to 1 to Q. Okay, but during reset, okay, as you can see, the green highlight shows when non-reset, the clock rise will transfer D to Q. But when reset happen, immediately the Q become reset. And then during the reset time, the Q stay 0 because reset will take effect whenever it is reset equal to 0. Then when reset become 1, then it will behave like a trigger, edge triggered flip-flop. When clock rise, then D transfer to Q. So another version of reset is synchronous reset. A D flip-flop with synchronous reset updates its output based on D, in other words, transfer D to Q based on the rising edge of the clock. The reset operation occurs when the clock signal is active. In other words, the reset is synchronized by the clock. So if synchronous reset is required, then you cannot put the negative edge reset in the sensitivity list. So we have to remove this, but the rest of the code the same as the previous one, where now when if statement is checking the reset, and if reset equal to 0, Q will only get 0, Q will only be reset when clock trigger to the positive direction. Okay, so this make the reset behave synchronously. So as you can see, when reset equal to 0 here, Q doesn't drop to 0 immediately because it is not a synchronous reset. Instead, it is a synchronous reset that it will wait for the coming clock rise, then only the reset take effect. Okay, that's why we call it synchronous reset. Okay, the rest of the behavior is similar with the previous example. We can expand how we describe D flip-flop to multiple bit register. Say you want to describe a 4-bit register. 4-bit register just consists of 4 flip-flops separately, okay? But they share the same, the common signal like clock signal and reset signal. Each of them still have their own input like D1, own output Q1, okay? So you can use the same code like how you code the single D flip-flop, but making sure that you have the vector showing that the D is 4 bits, Q is 4 bits, representing there are 4 flip-flops. If you want to have the reset, which is active low for the register, just make sure that you add the reset in the sensitivity list and the reset behavior. So the multiple bit register that load in the data is very useful in the application such as the arithmetic based application. So we have the register called load register, where it has the additional input, something like enable input, that we call load input. A load register is used to store the result of an operation. For example, a result from the adder called sum. It come out here, but it may not be used immediately. We want to store it first until it is used later. It is needed later. So the sum, when the sum is ready, then we need to activate the signal load so that the correct summation or the correct answer of the adder is loaded to the register. So the structure of load register looks like the one shown on the right hand side, where it consists of flip-flops and multiplexer. The multiplexer is to select whether the register should load a new value, D3, D2, D10, D0, or it should take the old value from Q3, Q2, Q1, Q0. In the case where it need to load the result from outside, for example here from the adder sum, then the load signal is on, then the multiplexer will select the answer of the adder to be stored by the register. But if there is no need to load the new answer to the register, then the load should be stay 0, so that the current value in this register will be looped back to each of the flip-flops so that it will hold. It will put the register in a hold mode, keep holding the old answer of the summation. Next, let's look at another type of register, which is shift register. A shift register shifts the bits of the input value one position to the right on each clock cycle, storing the result progressively in 4 clock cycles until the entire value is shifted through the register. For instance, we want to shift in 1010. Then what happens is first we will put the first bit 1 in the shift register input. When clock trigger entering the clock cycle 1, then the shift will happen where bit 1 will shift to inside into the first flip-flop, and the second bit 0 is getting ready at the input. When clock trigger again, the shift will happen where the first bit 1 will shift to Q2 and the second bit 0 will shift to Q1, and the new bit, the third bit 1, will stand by at in. And this happened until after the 4 clock cycles later, you'll see the 1010 is completely shifted into the registers and stored at Q1, Q2, Q3, Q4 as 1010. As you can see here, shift register have a very simple connection from one flip-flop to another flip-flop. However, when it involves flip-flops, the timing analysis normally is very important. And for this example, timing analysis for a shift register is important to ensure the data is correctly shifted and stored at the appropriate time without error, especially when dealing with clock signals, setup time, hold time. For example, currently we have bit 0 at Q1, bit 1 at Q2. So timing analysis need to be done so that it fulfill the setup, hold time, and timing criteria, such that the error like this, the shifting will happen like this successfully. So we don't want like the shift of the 0 that take over and override the shift of 0 from Q1 go to Q2 too fast until it override the 1 and 1 doesn't have enough time to shift to Q3. So we don't want such error happen. So to prevent such error, that's why timing analysis come into that picture. Okay, first we need to understand some important terms when we want to talk more about timing analysis. First is clock period. What is clock period? Clock period is the duration of time for a complete clock cycle. Right? Here 0 changing to 1, and before it repeat again the same pattern 0 to 1, that is the clock cycle time. Setup time is the duration of the time when the data D need to be stable at the input D before the clock age. So this window of time is called setup time. Hold time is the duration where D need to continuously stay stable after the clock age. So this window is called hold time. And lastly, the propagation delay means the time taken counting after the clock age. Yeah, here after clock age, we count how long the time taken for D to propagate to Q. Okay, for D to propagate to Q. So normally you'll see that the arrow is drawn from the clock pot to Q, showing the propagation delay. But actually, it means when clock age happen, when clock falls, when clock rise, starting from the point when clock rise, we count how long it takes for the data to move from D to Q. That is what we call propagation delay. It normally have mean value and max value because the delay for every circuit of the identical design will be slightly different due to process variation. Okay, so there's a range for propagation delay. Say you buy 10 flip-flop chips, but not all the flip-flop chips exactly have the same propagation delay. There's a range. Okay. Okay, assuming there's no clock skew or clock delay happen to all the clock wire here. Okay, and the hold time is normally smaller than the propagation time, and the clock period is wide enough or long enough before the next clock age, it is generally guaranteed that there will be no setup or hold time violation for a shift register. That means what I want to explain about the two things here about the timing analysis for shift register, because the hold time normally is shorter than propagation. That means 0 will take longer time to reach Q2. So by the time it reach Q2, the 0, by the time the 0 reach Q2, the signal 1 has gone through the hold time window. Okay? Because as illustrated here, when the clock age trigger, 0 start to move. Okay? And before it reach Q2, the whole time duration or window already passed. So it is safe for 1. 1 is still staying at Q2 when 0 is still halfway moving or propagating to Q2. By the time it reach Q2, because it's longer than hold time, so it's already past the hold time window. So the signal 1 already stay long enough at Q2, so the signal 1 doesn't violate the hold time violation corresponding to this flip-flop, okay, for the propagation. And then if the clock period is long enough, then this 0 will reach Q2 earlier, which is it will reach before the setup window starts counting towards the clock at the next clock edge. So in other words, when this 0, when reaching Q2, because the clock period is long enough, then by the time the bit 0 move from the Q1 to Q2, it still will reach earlier, okay, which is before the setup window happen or start to count towards the next clock edge. Next, let's look at how we code the shift register in Verilog. Okay, look at the 4-bit shift register that consists of 4 flip-flops connecting in as shown here. So when you do the coding, you can use always block post each clock, and Q1 will get signal from in. Okay, Q1 gets signal from in, Q2 gets signal from Q1, Q2 gets signal from Q1, and so on. However, always block is a sequential block where the execution will be sequentially taking place. So if you use the normal sign of the equal sign, which we call blocking assignment, okay, this equal sign means blocking assignment. So when the execution happens from the first line until the next line, this line by line will be evaluated, and assignment will happen to the left, okay, line by line. Okay, so that means in value will move to Q1 after this line. The same value in that moved to Q1 will move to Q2 after this line. In the next line, the same in value that moved to Q1 and Q2 will move to Q3, and so on. So at the end, what you will get is not a shift register. Instead, it is just a single D flip-flop where the output is Q4 and it will get the signal from in. So if you want to code shift register using blocking assignment, you have to carefully order the transfer of the data. So if you reverse the order where you say Q3 first move to Q4, then only Q2 move to Q3, then only Q1 move to Q2, and so on. So when the compiler read in this sequence, then it will successfully synthesize a 4-bit register shift register for you. Okay. So to play safe, actually you can choose to use another assignment, which is this arrow and equal. We call non-blocking assignment. Non-blocking assignment will evaluate the signal on the right-hand side line by line, and it will only transfer the result of the right-hand side to the left side at the end of the always block. So if you use non-blocking assignment, you don't need to take care of the order of the assignment, and you just need to make sure in the source and the destination correct. Okay? Source is in, destination is Q1. Okay, in go to Q1, source Q1 go to Q2, Q1 go to Q2. Then by using non-blocking assignment, then this coding will also give you the correct 4-bit shift register. Another version of shift register is called 4-bit parallel access shift register. So this register has 2 modes where it can play the role of load register, and it can perform shift mechanism as well. So it consists of flip-flops and marks. Normally when you have multiple modes, you need marks to select the mode. Okay? So if let's say you put 0 to the select signal, so you will see here 0 will choose the serial input to the first flip-flop. The second marks will choose the output of the first flip-flop to the input of the next flip-flop. So this will put the circuit into the shift register mode. But if you change the select signal to 1, then the first marks will choose the parallel input, go to the D flip-flop. All the marks will choose the data coming from the parallel input to the D flip-flop. And since every flip-flop has its own output, then when putting select signal equal to 1, it will put the circuit into a load register mode where the data is loaded, 4-bit data is loaded into the 4 flip-flops. Counter. Counter is straightforward in Verilog coding. Say if you want binary up counter for 4 bits, then you code start with the always block, like how you code for flip-flops, but the behavior under it is you use plus to increment the count. So if it is reset, then the count will become 0. Otherwise, it will be just increment. You can state using Q plus 1. Similarly, you can change the code for decrement. change the sign from plus to minus. And lastly, you have a counter of two modes, is up and down. That means you have a signal called up that can control whether you want the counter to increment or you want the counter to decrement. You can even have a counter with arbitrary sequence or a counter that count any number or you like, and you can determine it by describing the sequence in the Verilog code. In this case, you can use case statement. So case statement will describe the transition of your counter count. Say the currently Q is counting 1, then you can tell here next what happened to the Q. So after counting 1, if as based on the state diagram of the counter, after counting 1, you want the next count to be 3. Then you can describe here Q when if Q equal to 1, then the next Q should be 3. Okay. If Q equal to 3, then the next 3 should be 0, and so on. So you can code counter using case statement as shown here. So I think that's all for the lecture today about the latch, flip-flops, register, and counter, and how to code them in Verilog. Thank you.